So the man who wrote Redis, one of the most deployed pieces of infrastructure software on the planet, 1B, just published an LLM inference engine written in pure C, not Python, not PyTorch, no CUDA framework, just C. And according to Geeky Gadgets, it runs a 284 billion parameter model, one that starts life at roughly 568 gigabytes. In a 76 gigabyte memory footprint at up to 26 tokens per second. That 26 is a reported best case, by the way. We'll get to the fine print. The project's already pulled in over 13,000 stars on GitHub. Now, on paper, this shouldn't work. You can't just zip a 568 gigabyte model down to roughly 81 gigabytes on disk and expect it to still think. Except that's more or less what a quantization approach called Dwarf Star does. So this video is about the 3 tricks that make it possible: the model architecture, the quantization, and the engine itself. Plus the fine print nobody puts in the headline, because runs on a laptop is doing a lot of work in that sentence. Let's start with the model, because this story doesn't work with just any model. On April 24th, 2026, DeepSeek released the DeepSeek V4 family. 2 headliners. DeepSeek V4 Pro is the monster. 1.6 trillion total parameters, 49 billion active. And then there's the one we actually care about today, DeepSeek V4 Flash. 284 billion total parameters, 13 billion active. And that word active, that's the whole game. Flash is a mixture of experts model. Instead of running every parameter for every token, it routes each token to a small slice of the network. So only 13 billion of those 284 billion parameters are actually working per token. That's under 5% of the model doing the job at any given moment. On top of that, it ships with a 1 million token context window. And here's the part that made the open source world sit up. It's released under an MIT license. Anyone can grab the weights, quantize them, and build whatever engine they want around them, which is exactly what happened. Okay, trick 1 lives inside the architecture itself before anyone touches a single bit of quantization. DeepSeek V4 uses a hybrid attention design, compressed sparse attention, or CSA, paired with heavily compressed attention, HCA, and the two get wired together with something called manifold constrained hyperconnections, MHC for short. Honestly, you don't need to hold all 3 names in your head. Here's what they buy you. At million token contexts, single token inference costs about 27% of the flops of the predecessor model. That's attention at roughly a quarter of the compute price. And the KV cache, the memory that grows as your context gets longer, the thing that usually eats your RAM alive, drops to about 10% of what the previous generation needed. So before quantization even enters the picture, this model is architecturally cheap to run at long context. And that's the part most headlines skip. This model wasn't shrunk after the fact. It was built to shrink. Trick 2 is the compression itself, an approach called Dwarf Star. And the core idea is honestly pretty simple. Not all bits are equal. Naive quantization treats every layer the same. Squash everything down to 4 bits or 3 and hope for the best. Dwarf Star doesn't do that. It assigns different bit depths to different layers based on how sensitive each layer is to losing precision. Layers that can take brutal compression, they get brutally compressed. Layers that can't, don't. In the setup, Geeky Gadgets reports, the expert layers, the vast bulk of a mixture of experts model, gets squeezed all the way down to 2-bit precision. But the routing layers, those small components that decide which experts handle each token, stay at 8-bit. Because if you get the routing wrong, everything downstream falls apart. So that's where the precision budget goes. Average it across the whole model, and you land at roughly 2.3 bits per parameter, about 7-to-1 compression. And that's how 568 gigabytes becomes roughly 81. And just to be clear, this per layer philosophy isn't unique to Dwarf Star. The broader ecosystem is doing the same dance. Unsloth publishes dynamic GUF quantizations of this model, ranging from 92 gigabytes at 1 bit all the way up to 162 gigabytes for the Q8_K_XL variant. Their recommended sweet spot is a 3-bit quant called UD-IQ 3_XXS, 103 gigabytes on disk, needing about 110 gigabytes of RAM to run. Keep that 110 gigabyte number in your head, because it's going to matter a lot when we talk about what hardware actually clears the bar. But notice the pattern running through all of these. Spend your bits where the model is fragile and starve the layers that can take the hit. Which brings us to trick 3, the engine. Salvatore Sanfilippo, Antirez, the creator of Redis, wrote a custom inference engine for this model called DS4 in pure C. And pure means pure. No Python runtime, no PyTorch, no CUDA framework underneath. Now, let's be precise about who did what here. The reporting credits Sanfilippo with the engine, not with inventing the quantization method, and he doesn't work for DeepSeek. What he built is the code that takes those surgically quantized weights, 2-bit experts, 8-bit routing, and executes them fast. Per Geeky Gadgets, the result runs at up to 26 tokens per second, best case, in a 76 gigabyte memory footprint. And if you know Redis, it's hard not to see the same sensibility at work here. A small, handwritten C codebase, obsessive about memory layout, doing exactly the work required and nothing else. Think about it. Generic tooling has to handle every model ever made. A handcrafted engine only has to handle this one, so it gets to exploit every quirk of this exact architecture. The open source world noticed too. The project's drawn over 13,000 GitHub stars. All right, now the fine print, because runs on a laptop, deserves an asterisk the size of the model. First, the hardware floor. Running this quantized 284 billion parameter model locally requires, at minimum, a MacBook Pro with an M4 Max and 128 gigabytes of unified memory, or an NVIDIA DGX Spark. Remember, the recommended quant needs about 110 gigabytes of RAM. That's why 128 gigabyte machines are the entry point, and why your 16 gig laptop is not invited. Second, the speed spread. The reported numbers cluster into tiers, roughly 3 to 6 tokens per second on an M4 Max, 6 to 10 on an M4 Ultra, 15 to 30 on a DGX Spark. So that headline figure of 26 tokens per second, it sits at the top of the range. It's a best case reported number, not what a MacBook owner should expect. On an M4 Max, you're looking at output around reading speed, not a fire hose. One last practical note if you do run it. The recommended sampling settings are temperature 1.0 and top P 1.0. So if most people can't run it locally, why does this matter to everyone? Because of what it does to the price of intelligence. DeepSeek prices V4 Flash's API at 28 cents per million output tokens and markets it as delivering roughly 90 to 95% of frontier model quality at around 1% of the price. And the benchmarks behind that pitch aren't nothing. 91.6 on Live Code Bench, 79.0 on SWE Bench, verified. Now, take the marketing framing with appropriate salt. Those are the company's own comparisons. But here's the structural point, and this part is analysis. When frontier class weights are MIT licensed, compressible to roughly 81 gigabytes, and runnable by one determined C programmer, the floor under inference pricing changes. If a provider charges too much, well, the weights are right there. The real story isn't that everyone will run this at home. It's that the option credibly exists, and options like that tend to discipline markets. So, how did the creator of Redis get a 284 billion parameter model running on a single machine? The answer was 3 layers deep. And now you've got all 3. Layer 1. Architecture. DeepSeek V4 Flash engages only 13 billion of its 284 billion parameters per token. A mixture of experts' design that makes most of the model dead weight most of the time on purpose. Layer 2. Quantization. Dwarf Star assigns bit depth layer by layer based on sensitivity, averaging about 2.3 bits per parameter, collapsing 568 gigabytes into roughly 81. Layer 3. The engine. Sanfilippo's DS4 in pure C runs those 2-bit experts with 8-bit routing at up to 26 tokens per second, best case inside 76 gigabytes. Each layer does surgical work that generic tooling can't, and stacked together, they turn an impossible headline into an engineering receipt. And here's your honest checklist. If you're tempted, 128 gigabytes of memory gets you in the door at 3 to 6 tokens per second on a MacBook M4 Max. This is where hand-tuned systems code and frontier-class weights just met. And Neural Stack will be covering what happens next. Subscribe if you want the breakdown when it lands.